Imagine you're scrolling through a social video feed. The next clip you watch might be there because a close friend liked it, because it came from a creator you follow, because someone shared it in a group you belong to, or simply because it looks semantically similar to something you watched last week. Traditional recommendation systems tend to flatten all of these different social signals into a single dense vector, and in doing so, they lose the ability to say which specific relationship actually mattered for a given recommendation. The paper we're looking at today, called ConnectionMind, comes from Meta and tries to fix exactly this problem by treating recommendation not as an embedding lookup, but as an act of reasoning across a social graph, guided by a large language model, or LLM. The motivation comes from three empirical patterns the authors observed in Meta's production logs. First, a substantial fraction of engagements are socially connected, meaning content flows through friendships, groups, and creator follows rather than existing in isolation. Second, that social relevance is highly concentrated. Only a small handful of your friends, groups, or followed pages actually predict what you'll engage with. And third, that concentration is stable over time. The same friends keep mattering. This immediately suggests that indiscriminately aggregating over all of a user's social neighbors, which is what graph neural networks and diffusion-based social recommenders typically do, is going to inject a lot of noise. What you really want is a system that can selectively pick the right social evidence for each recommendation, almost like a detective following a specific chain of clues rather than dusting the entire room for prints. Prior social recommender systems generally fall into a few buckets. There are matrix factorization methods with social regularization that encourage friends to have similar embeddings. There are graph neural network approaches like GraphRec and MHCN that pass messages along both the user-user social graph and the user-item interaction graph. And there are diffusion models like DiffNet that recursively propagate preferences across social links. All of these work reasonably well, but they share the same fundamental limitation. They collapse heterogeneous, multi-relational evidence into dense embeddings, which makes it hard to know why a recommendation was made and hard to be selective about which social signal to trust in a given context. Meanwhile, LLM-based recommenders like P5 and BigRec bring in semantic reasoning but typically ignore social structure entirely. Connection. Mind sits at the intersection of these two worlds. The authors build a heterogeneous graph where the nodes are users, pages or creators, and items, and the edges encode friendships, behavioral similarities between users, follows, group memberships, group shares, creator posts, item co-watches, and semantic item similarity. Every video in the graph gets converted into a compact text summary by running optical character recognition on any on-screen text, automatic speech recognition on the audio, dense visual captioning through a video LLM, and then compressing all of that into a paragraph with another LLM. Users and pages get similar textual summaries derived from the content they've engaged with or published. So every node in the graph carries a readable semantic profile. Now here's the key reframing. Instead of asking, what's the embedding of this user and how similar is it to each item, ConnectionMind asks, starting from this user, what's a path through the graph that leads to a good item? A path might look like user followed by friend edge to another user followed by watched edge to a video. Or it could be user, group edge, group, share edge, item. Each path is a piece of interpretable evidence. Think of it less like a search engine ranking documents and more like a research assistant tracing a citation trail. The problem, of course, is that the full graph is astronomically large. So the authors first sample compact task-relevant subgraphs around each target user, keeping only the top few neighbors per relation type based on edge weight and semantic similarity. The reasoning itself is done by an LLM policy that explores this subgraph step by step. At each step, the model sees the current set of partial paths, the frontier nodes at the tips of those paths, the available outgoing typed edges, and the textual profiles of the nodes involved. It then outputs a structured action in a fixed JSON-like schema that specifies which paths to extend and which items to surface as recommendations along with their evidence traces. This continues until the paths are exhausted or a maximum depth is reached. Training happens in two stages. First, supervised fine-tuning. For each real user item engagement in the logs, the authors compute the shortest paths from the user to the engaged item in the sampled subgraph and treat these as gold reasoning trajectories. The LLM is trained with a standard token-level negative log likelihood objective to imitate these step-by-step decisions. This warm starts the model so it produces schema-valid, relation-consistent expansions rather than free-form hallucinated text. Second, reinforcement learning. Even if every local step looks plausible, the full rollout might miss good items, so the authors optimize the entire trajectory with Group Relative Policy Optimization, or GRPO, against a composite rule-based reward. That reward has three parts: a format reward that penalizes invalid schemas or edges that don't exist in the graph, a final recommendation reward based on the F1 score between surfaced items and the true engaged items reachable in the subgraph, and a stepwise shaping reward that gives partial credit when the expansion moves toward reachable positive items. The weights are set to prioritize recommendation quality while still enforcing valid exploration. On public benchmarks like Delicious and Foursquare, ConnectionMind substantially outperforms a wide range of baselines, including matrix factorization with Trust, GraphRec, MHCN, SEPT, DiffNet, and the LLM-based Big Rec. Recall at 5 on Delicious jumps from around 2% for the best GNN baseline to over 6% with an 8B Llama backbone. The ablation is instructive. A raw Llama 3.23B with no adaptation achieves near zero recall. Supervised fine-tuning alone gets you most of the way there, and reinforcement learning provides a meaningful additional lift. But the real headline is the production deployment. Because running an 8B LLM for every recommendation request at metascale is infeasible, the authors use a hybrid teacher-student setup. Heavy users, the top 5 to 10%, get the full LLM treatment, while the rest of the traffic is served by a lightweight graph neural network student that's been distilled offline on the paths the LLM discovers. In a multi-week A/B test on tens of millions of users, they see a 0.33% lift in exposure diversity, a 0.43% lift in watch time, and a 0.22% lift in video sessions. At metascale, these small percentages translate into enormous absolute gains. That said, there are some real limitations worth calling out. The recommendation reward during reinforcement learning is computed only against positives reachable within the sampled subgraph, which means the subgraph sampling quality upper bounds what the policy can ever learn. If a great item lives outside the sampled neighborhood, the policy can't be rewarded for finding it. The teacher-student split also means most users are not actually getting LLM reasoning at serving time, so the interpretability benefit is somewhat concentrated on the heavy user cohort. And while the paper emphasizes explainability through evidence paths, there's no formal user study on whether these paths actually help users trust or understand recommendations. Finally, all evidence about the 3 empirical patterns motivating the work is reported qualitatively due to privacy constraints, so we're partly taking the authors at their word. Now let's walk through some questions you might have after hearing all of this. First, why use an LLM here at all, instead of just a bigger graph neural network? The answer is that the action space combines 2 very different kinds of reasoning. The model has to make structural decisions about which typed edge to follow, and it has to understand the semantics of what's on the other side of that edge, like a video's actual content or a creator's style. LLMs are unusually good at absorbing textual node descriptions and making context-sensitive choices based on them, whereas a pure GNN would have to encode all that semantics into fixed embeddings up front and lose the ability to reason about it dynamically per query. Second, why do supervised fine-tuning and reinforcement learning both, rather than just one? Supervised fine-tuning teaches the model the interface, meaning how to output valid JSON, how to respect edge types, and how to walk the graph without hallucinating. But it only supervises individual steps against a single gold shortest path, ignoring that many valid paths might reach a good item. And it doesn't know about item-level recommendation quality across the full rollout. Reinforcement learning fixes both problems by rewarding the entire trajectory based on final recommendation F1 and by giving the model freedom to discover paths that aren't in the supervised set. Third, how does this handle the cold start problem for a new user with sparse history? This is actually where the graph structure shines. Even a user with few personal interactions typically has social connections through friends, group memberships, and follows, and each of those neighbors carries rich textual profiles. The LLM can reason semantically over those neighboring profiles and surface items via social paths even when direct user item history is thin. The A/B test results showing improved catalog diversity and long-tail exposure suggest this is working in practice. Finally, thinking about how this transfers to large-scale recommendation systems in general, the most transferable idea is the teacher-student hybrid inference pattern. Running LLM reasoning per request at billion-user scale is a non-starter, but using LLMs offline to discover high-value metapaths and then distilling that pathfinding logic into a lightweight GNN that runs in milliseconds is a genuinely practical recipe. Any large-scale platform with rich relational side information, whether that's e-commerce with product taxonomies and seller networks, professional networks with company and skill graphs, or music platforms with artist collaborations, could adopt this pattern to inject reasoning into candidate retrieval without breaking latency budgets. The other transferable insight is treating recommendation as evidence path generation rather than embedding similarity. In production ranking stacks, this gives you two concrete wins. You get interpretable traces that help debugging, monitoring, and building user-facing explanations like recommended because your friend watched this, which are increasingly important for trust and regulatory compliance. And you get a natural mechanism for selective social signal use, which mitigates the noise problem that plagues broad neighborhood aggregation in production social GNNs. The rule-based reinforcement learning reward design is also worth noting because in real recommendation systems where you have clean engagement signals and structural constraints, rule-based rewards can be substantially more stable than learned reward models and easier to iterate on when product priorities shift.